This video is about the loudness of sound. It corresponds to section 26.3 of Applied Analog Electronics. Now, sound, if you may remember, is a fluctuation in air pressure. And we measure that traditionally in pascals. Problem is that human hearing, like many human senses, is not really linear. That is to say, if we double the pressure, it doesn't double the loudness of the sound. In fact, each doubling in the pressure results in about the same constant increment in how loud the sound appears to us. So another way of saying that is that human hearing, the loudness of sound, is essentially a logarithmic function of the amplitude of the sound. So we have got a traditional way of handling that sort of logarithmic response, and that is to use decibels. Decibels are just a logarithmic way of expressing any ratio. And if we have a ratio, say the amplitude of some signal divided by some reference, so that we've got two things in the same units, this is a unitless ratio, we can take log base 10 of that, multiply by 20, and that is the number of decibels that this ratio corresponds to. Now, when we're talking about sound, we'll express it in terms of dB SPL, sound pressure level. And basically all that means is that it defines what our reference amplitude is. And that reference amplitude is 20 micropascals RMS. So it isn't, strictly speaking, an amplitude, it's an RMS measure of the signal, root mean square, and we talk about that in more detail in another video. So this quantity is a pretty small one. This is the amount that we would get with 0 decibels, because if we had this amount coming in, then A and A ref are the same. The ratio is 1. Log base 10 of 1 is 0. 20 times 0 is still 0. So 0 dB, this is the 0 dB level. And quite often the reference value for anything that's expressed in decibels would be given in terms of 0 dB is, and then give a value, and that's the reference value. So what sort of sound levels do we normally deal with? Well, ordinary speech, kind of like what I'm doing now, is probably around about 60 dB for the sound pressure level. All right, how big is 60 dB? Well, we can kind of turn this thing around and say what we've got is 10 to the 60 over 20 times 20 micropascals, which is, that's 1,000. 60 over 20 is 3, so 10 to the third is 1,000. So that's 20 millipascals. So 60 decibels sound pressure level corresponds to 20 millipascals, and again, that's an RMS measure of the sound pressure level. So it's very simple to convert back and forth between sound pressure levels expressed in decibels and pressures expressed in pascals. Now, you may notice that this is millipascals, and when we were looking at stuff with the blood pressure sensor stuff, we were looking at kilopascals. There's a huge difference between them. And that's why if you tried to use your pressure sensor as a microphone, you didn't end up hearing anything with it, because it was being sensitive to fluctuations of a few pascals, and the fluctuations you were getting from sound in the room and stuff was only on the order of 20 millipascals, way too small to be visible with the pressure sensor. And that's why we have microphones, which are very sensitive to these tiny fluctuations in pressure, but which are designed to be insensitive to sort of barometric pressure changes, which are slower and very, very much larger. Okay, if this was all we had to do, we'd be done, and loudness would be a very simple phenomenon. The trouble is, human hearing is not equally sensitive at all frequencies. This 20 micropascal RMS, that's really appropriate at 1 kilohertz. But at much lower frequencies, like down at 20 hertz, our ears aren't nearly as sensitive. It takes a much larger pressure variation to sound equally loud to us. And so when people are doing stuff that's intended not for physical measurements of energy or something like that, but are intended for their impact on human beings, so how loud is it going to sound to people, they add a weighting to the decibel scale, which is the same thing as multiplying the amplitude by an amount. And the standard weighting scheme that's used is called the A weighting scheme. It was developed a long time ago, I think 1936. And what it does is it produces the most sensitive values at about 2 kilohertz. And I think there, or 2.5 kilohertz, and there it's about 1.27, 1.3, something like that, decibels higher than it would be at 1 kilohertz, where it's by definition 0. So there's no adjustment at 1 kilohertz. As we get to lower and lower frequencies, the human hearing gets much less sensitive, and so the A weighting gives you a larger and larger negative amount. So what we do is we look at the amplitude, do the calculation for how many decibels we get with that amplitude, and then add on a number that's taken from this curve. So at 100 hertz, it looks like we're taking off about 20 dB. When we get down to 10 hertz, we're taking off 70 dB. And that corresponds actually reasonably well to how good human hearing is for pure sine wave tones in this lower frequency range. One thing the A weighting scale is not so good for is high frequencies. Because if you could take a look at this plot, we're going up to about 20 kilohertz here, and it's only about 10 decibels down at 20 kilohertz. But humans basically don't hear at 20 kilohertz. So it should be, minus 80, minus 90 dB here. And it's not. And the reason for that is probably because of what the original A weighting scale was set up for, which is matching human hearing for lower frequencies for the most part. The sorts of things you get, the rumble of machinery and stuff, diesel engines and stuff like that in the 1930s. And they weren't so worried about the high frequencies. It was very difficult to get, with the electronics technology of the 1930s, a very sharp cutoff filter. And so dropping from being really sensitive at 2.5 kilohertz to completely insensitive at 20 kilohertz was difficult. And since they didn't care that much about that part, they decided just to ignore it. Unfortunately, dBA weighting is built into a lot of noise ordinances and other regulations, and so we're stuck with it even though it does a really pretty crummy job at high frequencies. A lot of decibel meters and stuff like that, sound meters, don't actually cover beyond about 8.5 to 10 kilohertz because the A weighting scale gets pretty bad at the higher frequencies, and it's misleading to use it. Let's take a look at an example of using the A weighting scale. This example is from the book, just to see how you would figure out how much pressure is there if we've got a signal that's specified using the A-weighted sound pressure level. Okay, so the example there is that we have got a 40 dB signal, A-weighted, and it's a sine wave at, I think I said 200 hertz. Okay, so what we're going to have to do is figure out what's the amplitude of this waveform. It's a sine wave, so things should be all very simple. It's a frequency range, 200 hertz, where it makes sense actually to use dBA weighting. What we have to know, first of all, is what was that curve? So we were looking at this curve. What is it at 200? And you could try and measure it off of a graph like this one. It's hard to get a good job, get good numbers that way, and a few dB can make a difference here. So what I recommend doing is either using the formula, which is huge, or more simply, using one of the internet calculators. There's lots of them out there. This formula is, public domain, has been for a long time. It's very easy to find calculators that'll tell you how many dB is the correction at 200 hertz. And I did that. I don't remember whether I did it by calculating with GNU plot from the formula or whether I did it by using one of the internet calculators, but it should come out about the same. And I believe it was minus 10.847 dB at 200 hertz. So let's do two calculations. One is, what would be the pressure level if this hadn't been dBA, if this had just been straight decibels and they hadn't had the A correction? Then we would have had 10 to the 40 over 20 times 20 micropascals RMS, which is, well, that's just 100 there, so that's 2 millipascals RMS. That's with no weighting. But we did have a weighting here, so we're going to have to do 10 over, well, we have to undo this minus 10 dB, so we're going to have 50.847 over 20 decibels, and again times the 20 micropascals. All right, let me grab my calculator here and do 50.847 all right, the multiplier here is 348, and we've got 20 micropascals, and let's look at that in engineering notation. So we've got about 6.97 millipascals RMS. And that's the pressure variation we've got. But I just looked back and see what the working example asked for. It asked for the amplitude. It didn't ask for the RMS value, it asked for the amplitude. Now, luckily, this is a sine wave. And so for sine waves, we have a crest factor of square root of 2, which means that the amplitude is square root of 2 times the RMS value. And we'll talk about RMS more in another one of these videos. I think it's coming up when we deal with the amplifier. Okay, so if we multiply this by square root of 2, I now get that that's plus or minus 9.86 millipascals as the amplitude. And that's a milli here, not a micro or anything else. Okay, so we're looking at about 10 millipascals. Still obviously way, way smaller, even with this correction we've got, way smaller than what you would have from using a DC pressure sensor. Where you'll be using this sort of calculation is in figuring out how much signal am I going to get from my microphone. Microphones are specified in terms of how many decibels of gain they have, usually negative because there's less coming out going in. And so you're going to need to know, well, how much pressure variation do I have in decibels? You can do all your calculations in decibels because essentially all your gains are multiplied. So if you specify the gains in decibels, because everything is now logarithmic, you just add things. But you can figure out how big is your signal, how much sensitivity does the microphone have, and so how much signal will I get out of the microphone. And that'll be coming up when we do the next video.